Hello, this is Mr. McGovern, and this is the 7th video in the Momentum and Impulse series, and the last one where I look at an NCEA problem. I've chosen this from 2017. It's question 1, A, B, and C. So in the situation we have two roller skaters, and they're skating in the same direction. Katie's moving faster than Aroha, and they collide into each other and then move off together at the same constant speed. So straight away when I see collision, I'm thinking momentum. How can I use momentum or impulse to solve these problems? So what do they ask me? So they say, first of all, what physical quantity is conserved during the above inelastic collision between Katie and Aroha? State any assumptions you've made. So total momentum is conserved, the first one. Not momentum, because Katie's momentum is going to decrease and Aroha's momentum, I think, is going to increase, but the total momentum of the system is definitely conserved. So what assumptions have I made here? So we can go back to video 6 if this doesn't make any sense. But effectively, total momentum is always conserved as long as there's no unbalanced forces acting from outside our system into our system. So a really concise way of saying that is just saying there are no unbalanced external forces. And that, if that's the case, then total momentum is definitely conserved within our system. All right, the second question for, I think this is a merit, is calculate the combined velocity of Katie and Aroha as they skate off together after the collision. So I've just made this nice and small so I can fit in momentum bar charts. So I like to do momentum bar charts to sort my equations out first. To find a positive direction, everything's moving to the right, so why don't we call right positive? Makes sense. My momentum bar chart for before and afterwards, and so before I have Katie skating along. She has 65 kgs, 8.5 meters a second, so I'm going to give her some momentums, and Aroha is less mass, less velocity, so I'm going to give her less momentum. So why don't we give Katie 3 momentums and Aroha 2? They're not obviously exact, it's just to get a general idea of what's going on. Afterwards they're stuck together, so why don't we just call them combined or coupled? And we know their combined mass is 115 kgs because that's 65 plus 50. We don't know their combined velocity. They have to have 5 momentums because the momentum bar chart shows us that the total momentum before equals the total momentum afterwards. So I have 3 and 2 momentums before, which is a total of 5. I have 5 afterwards. Using this momentum bar chart, I can write myself a little equation. The momentum of Katie and the momentum of Aroha added together gives me the total momentum when they're combined after the collision. 3 plus 2 equals 5. That's what that graph's showing, and now I've written it as a physics equation. We also know momentum is equal to mass times velocity, so I've got that ready as well. So I've used my bar charts to get an equation. I can kind of leave them behind now, and my equation is the same. I still know P is the symbol for momentum is equal to mass times velocity. And what I'm going to do is I'm going to take that first equation there, and instead of writing momentum of Katie or P of Katie, I'm just going to write mass times velocity of Katie. And then the same for Aroha. Instead of momentum, I've got mass times velocity of Aroha, and combined, mass combined times the velocity combined. And then put in all the values that I know. I know Katie's mass, I know Katie's initial speed, I know Aroha's mass, Aroha's initial speed, I know their combined mass, I don't know their speed. So simplify some of those on my calculator, I get something like this, and then divide both sides by 115 kgs, and I get 7.41 meters per second. So that's their combined velocity after they collide. Question 1, that was, by the way, was a merit question. This is also a merit question. As Katie collides with Aroha, they both experience a force due to the collision. The duration of the collision is 2.5. Calculate the size of the force experienced by Aroha. So we know from video 4, I think it is that the forces they experience are the same as each other, and that's Newton's third law. So I could work out the force experienced by Katie if I wanted, and it would be the same as the force experienced by Aroha. I don't think I need to, but that's just a little trick up my sleeve in case I needed to. So in collisions, and we're talking about forces, I'm going to probably use impulse. So force is the same, I've said that. This is my impulse equation. So each of these sides of the equation is called impulse. So force times the time you're in a collision for is impulse, but also change of momentum is also impulse. Now I've been given the collision time, 2.5 seconds, and I'm sure I can work out the change of momentum, so I should be able to work out force. So to work out the change of momentum of anything, we just need to work out what its initials and final momentum was. So Aroha These are the values we started with. She was going 6 meters a second. She's 50 kgs, so we get 300 momentums. And her final, because she's moving off with Katie at 7.41, we can times those two together and we get 370 momentum. So the change in momentum is always just final momentum minus initial. 370 minus 300 is 70 kilograms per meters per second, or 70 momentums as I like to call them. So now I've got the same equation I had before. I've got the change in momentum, 70. I know the time, 2.5, and I can just rearrange to find the force is 28 newtons.